All right, so this is our last section. So 10.2, it's very, very similar to 10.1. Hopefully you'll kind of see the pattern by now. Like I think it was 8.2, we talked about confidence intervals for population proportions. Then 8.3, we did the same thing for means. Then in 9.2, again, we did proportions. In 9.3, we did significance tests for means. Now, again, 10.1 was comparing two groups using proportions, and then 10.2 comparing two means. So if 10.1 made sense and all the chapter 8 and chapter 9 made sense, there shouldn't be anything really um, too profound in here. We're just going to use the same techniques. It's just basically more formulas and stuff that we got to kind of keep track of. Um, so again, basically the motivation for this again is exactly the same as proportions, except now we're trying to compare the means instead of proportions. Um, so here's a little example. It's not, I mean, where we don't really do much calculation or anything like that, but um, uh, to explore the sampling distribution of the difference between two means, let's start with two normally distributed populations having known means and standard deviations. Now, again, normally we're not going to know the means and standard deviations of the populations, right? Those are the parameters that we're trying to estimate using statistics. So, but the heights of 10-year-old girls follow a normal distribution. Um, 56.4 is the mean, and 2.7 inches is the standard deviation. And 10-year-old boys, 55.7 is the mean, and 3.8 is the standard deviation. So suppose we take an independent simple random sample of 12 girls and 8 boys of this age and measure their heights. What can we say about the difference in the average heights of the sample of girls and sample of boys? So that's an example of where we might want to compare two means. All right. So here they generate the, these samples 1,000 times. If you look at the sampling distribution for um, girls, it's the left one here, X bar F. The average sampling distribution of the X bar for males is in the middle, and then when I subtract, take X bar sub F minus X bar sub M, so girls average minus boys average, I get what's over here. So kind of looking at the picture here, it looks like the mean of this is a little bit bigger than 0, so it looks like um, the center is going to be a little bit higher for girls, which we expected, probably because of this number being higher than that number. Uh, but in general, um, again, we learned about for any two independent random variables, we can subtract the mean of the difference is going to be the difference of the means. And again, when I find the standard deviation, it's just going to be this the sum of the squares of the standard deviation. So um, same thing we've been dealing with. All right, so little information shape. If the populations that we're looking at are normal, then the standard distribution of the difference there is of the comparison is approximately normal. In other cases, we're going to use our good old large sample size, where we have more than 30 in each of them, or more greater than or equal to 30 in each of them. So center, again, the mean is just subtract the two means, and the standard deviation, this formula here. Again, kind of coming from the standard deviation formulas that we have and combined with this fact up here. So let's just take a look at an example. So a fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid dispensed by the machine, call it L, follows a normal distribution with mean 27 ounces and standard deviation 0.8 ounces. When medium, it's a normal distribution with 17 ounces and standard deviation of 0.5. And to test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of 20 cups filled with the large setting and 25 cups filled with the medium setting. Let's let X bar sub L minus X bar sub M be the difference in the sample mean amount of the liquid under the two settings. So what is the shape of the sampling distribution of X bar, the difference of the two? Well, since they're both approximately normal, right? Or since they're both normal, and normal, then this is going to be approximately normal. So um, since x bar L and x bar M, those sampling distributions um, are normal, therefore it must be normal. Find the mean of the sampling distribution. Show your work. Well, the mean is just going to be 27 minus 17. This is going to equal 10. And again, I probably should label it ounces. And then find the standard deviation. Again, we're just going to use this formula right here. So we get, for C, we get square root of, let's see here, 0.8 squared over 20 plus 0.5 squared over 25. And they do the calculation here, and that ends up being 0.205. And again, normally to use the standard deviation formula, we'd have to check the 10% condition, but we don't have to worry about that because we're not, sampling without replacement. So now we're going to use our t-distribution like we've done in the past. So since we don't know the actual values of the parameter, right? We don't know the values in the population. We're going to have to use our sample standard deviations. So it's the same idea, except instead of sigmas, we got s's. And remember, t, our test statistic, is going to be our statistic minus parameter over standard deviation. Kind of using that same formula that we've been using. And the same requirements that we've been using as well. So like I said, there isn't actually that much new in this. And what there is new, we're going to more or less use our calculators to do. So remember, this formula should look kind of familiar, right? We kind of set it up in general as our, our statistic plus or minus our critical value times standard deviation, basically. Now, here's the only thing that's kind of new is for our degrees of freedom, we are probably going to use the smaller of basically to take the smaller sample size minus 1, and that's going to be our degrees of freedom. We'll see our calculator can calculate it differently as well, but this will be conservative. If I pick the smaller of those two, that'll be a conservative estimate, so it'll be at least as good as that. So let's just take a look at an example here. So a preserve in Georgia is an old-growth forest of pines that survived in a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is how did the sizes of pine trees in the northern and southern halves of the forest compare? So they took a random sample of 30 trees from each half and measured the diameter in centimeters. Here are the comparative box plots of the data and summary statistics from Minitab. Okay, so based on the graph and the numerical summaries, write a few sentences comparing the sizes of longleaf pine trees. So again, I'm just going to say it in words rather than write it, because I'll show you what their answer is in just a second. But let's just look at the box plot. It looks like definitely the northern trees in general have smaller diameters than the ones in the south, because I mean, look at both the median and the mean of the south are substantially larger. The north has a slightly larger range and IQR, right? Remember the IQR is that right there, that length. So so the north, the data in the north is spread out a little bit more, and neither of the regions has outliers. And again, we're kind of using that SOX example. So we talked about spread, we talked about center, we talked about outliers, and shape. The northern is right skewed, and the southern region is left skewed. So that should just about cover that. And then B, construct and interpret a 90% confidence interval for the difference. Okay, so we'll do that in a second. Let's read what they say. Distribution yeah, northern sample skewed is right skewed, southern sample left skewed. Um, southern half have larger diameters. Yeah, so more or less we everything we said. The only thing we didn't really talk about was the 75% of southern trees have diameters that are above the northern sample's median. But you can see that again from this compared to this right here. So that's where they get that data from. But I don't think if you omitted that, that would be a big deal. All right. So we're going to state, plan, do, conclude, that 4-step process. So again, this is kind of I haven't really been making you do this too much, but make sure you define your parameters of interest and things like that. So we're trying to find mu1 is the true DBH of all trees in the southern half, and mu2 is the true DBH of all trees in the northern half. And we want to find mu1 minus mu2 at a 90% confidence level. All right, so it's random. We're good with that. 10%. You can safely assume that there are probably, since there are 30 in each sample, you can probably safely assume that there's more than 300 trees in each half of the forest. Wouldn't be much of a forest if it had, less than 600 trees in it total. So, and then normal large sample, again, the box plots, looking at these, I would say that these are strong evidence that it's not normal. So we can't use that. However, we have at least 30 in each sample size, so we're still okay. So remember, the conditions are either both of them are normal, and then we don't care how many there are, or if they're not normal, then if we have at least 30 in each sample, then we can say it's approximately normal. All right, so looking at this, so we have 30 in each. Remember how I talked about how we were going to pick the smaller degrees of freedom? Well, they're both 30, so we're going to pick DF to be 29. So that's just because 30 in the sample size, each sample size minus 1 gives me 29. And then we want to find where at a 90% confidence level. So we're going to look at in our table in your note sheet, you can 90%, or you can look at 0.05. Again, the reason why it's 0.05 and not 0.1 is because that's right here is 0.05, and so then using symmetry, that'd be 0.05. But so we use that with df equals 29. We look that up, and we get our t star value of 1.699. So now we just plug stuff in. Subtract our two means, plus or minus t star times the standard deviation, and we still need to figure out what the standard deviation is. So we're going to have, I know it says it all down below, but let's just write it out. We've got 34.53 minus 23.70, and that's going to be plus or minus t star, so 1.699, times the standard deviation, which is going to be, again, 14.26 squared over 30, plus 17.50 squared over 30. So I'll let them do that math, but that's where they got all that stuff from. And they get this as our confidence interval. Now we could do it on our calculators. Okay, so we got to go in here and do stat tests. Now we're looking at a confidence interval, and we're comparing two, and so it's going to be a 2-sample t. Beautiful. Again, we would use z if we knew that, if we were using actual population values, but we don't have those. We're using our statistics, so that's why it's t. And then we're going to use stats because we were given this information, and we've got our x bar 1 was 34.53. Standard deviation was 14.26, and we had 30. X2 is 23.7 and 17.5 and 30. Oops. Confidence level was 90%. No for pooled. We're not going to worry about that. And so notice If we compare our answer here, 3.93, 17.72. Again, that's just simply the reason for that. It's going to tighten it up a little bit because they were our calculator is able to calculate the degrees of freedom here. So that's a little bit less conservative. So that's kind of nice. Again, it's kind of more important to figure out, understand what we're doing. Like the math calculations that we're doing is not as important because our calculator can do it all. It's just kind of important to understand what we're doing exactly. So that's confidence intervals. Now significance tests. Again, we've talked about how those are closely related, and so we're going to do the same idea. Null hypothesis um, is that basically we subtract the two means, and that's what we suspect for our null hypothesis. So we're going to say that there's no difference between the two parameters. That's what our null hypothesis will always be. An alternative is that there's one's bigger than the other, or they're just not the same. So same again, everything very, very standard. And again, we talked about test statistic is this guy right here. We've used this already. So, and again, we're going to use the same degrees of freedom, smaller of n1 minus 1 and n2 minus 1. Or using our calculator, it'll give something different. So, again, all these are the same idea. It's just different formulas. So let's actually do it in practice. Make sure it makes sense. So, does increasing the amount of calcium in our diet reduce blood pressure? So, examination of a large sample of people revealed a relationship between calcium intake and blood pressure. The relationship was strongest for black men. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. So we had 21 healthy black men who volunteered to take part in the experiment. They were randomly assigned to two groups. 10 men received calcium supplement for 12 weeks, and while the control group of 11 men received a placebo that looked identical. It was double-blind. Response variable is the decrease in systolic blood pressure for the subject after 12 weeks in millimeters of mercury, and increase appears as a negative number. So here are the data. So that's kind of important. That's kind of, I mean, in order to help it match our intuition, that's kind of important. Is an increase appears as a negative number, and the way you might do that again is an increase in that blood pressure typically would be a negative, negative as in bad, not desirable result. All right, so do the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo? Carry out the appropriate tests to support your answer, and interpret the p-value you got in part A in the context of this experiment. Okay, so this one, notice they don't give us a confidence interval. So I think, again, 95% confidence, not interval, level, I meant to say. And 95% confidence is pretty good. So I would probably use alpha equals 0.05 for this. So again, that's just kind of a good go-to whenever you don't, it's not given to you in the problem. All right, so the null hypothesis is that there's no difference, so that the average is equal to 0. Alternatively, we want to know whether it does better. So instead of just saying not equal to there, what we're going to do is we want to have mu sub 1 minus mu 2 be greater than 0. So again, where that's the mu represents the decrease in systolic blood pressure. So we want that, if that's positive, then it's taking the calcium supplement is a good thing to lower that blood pressure. All right. And again, so use alpha equals 0.05. So random, they were a random, double blind, everything like that. Here, again, it's an experiment. So in experiments, we don't have to worry about the 10% because there was no sampling. And so we have small sample sizes. That's kind of a bit of a problem. So we need to look and see if they look approximately normal. So looking at calcium, um, this looks, I mean, it's slightly skewed to the right, but I would say not very strongly skewed at all. And again, similarly, looking at the placebo, it's slightly skewed to the right. But again, those are just very, very slightly skewed. So I would say no outliers, no, and it's not strongly skewed, so they look up like they could be approximately normal. So we will use our two sample t procedures. All right, so using our formula, we're just going to, let's see here. So unfortunately, with this data, and I'll show you how to do this on your calculator as well, but well, we already know how to get this info from it. But you plug all that into your calculator and you figure out that what the average is and what the standard deviation is for each of those. And we'll be able to see how to do it without even doing that. We'll do it all in one step on our calculator at the end of this. All right, so you plug all that in. So again, x bar minus x bar, so that's where that comes from. Minus, again, the null, this right here is the null hypothesis, and the null hypothesis is that they're the same. So that's where that 0 comes from. And then just plugging in the rest for the standard deviation. So we get t equals 1.604. All right, so again, we're going to pick the smaller of the two, and one was 11 and one was 10, so 10 minus 1 gives me 9. So we're going to look at where df equals 9, and we're going to try and find out where the value 1.604 would appear in our data using this column here. So it looks like it's between 0.10 and 0.05, and we can figure out what it is exactly, but it's definitely bigger than 0.05, right? It's between so it's between 0.05 and 0.1. So therefore, P is bigger than 0.05. So, and why does that matter? Because our alpha is 0.05. So from that, we can already say that we fail to reject the null hypothesis, right? We don't have convincing evidence that calcium caused the blood pressure to drop. Now let's see how to do it on our calculator. So we could just go into stat, edit, and 7, -4, 18. And I'll just punch this all in, pause and all right, so now I've punched it all in there. Now let me just show you how you could get these numbers here as well, just to remind you. So just to show you my lists, I punched them all in. First column was the top row, and second column was the bottom row. Now you can go into stat, calc 1var stats, and this will do it on L1, or if you want to be extra careful, you can say 1var stats L1. And there it tells me my x bar is 5, standard deviation is 8.74, and you can see those numbers right there. And then if I want to do it on the other one, I'm just going to do the exact same thing, stat, calc, 1var stats, and then list 2. And now you can see standard mean negative 0.27, standard deviation 5.9, and they match up. So that's how you could get that data, and if you're trying to do it by hand. But otherwise, we can also, this time we're doing a test. We're doing a t-test with two distributions. So let's go to stat, tests, two sample t-test. And now I'm going to do input is data. List 1, L1, L2, frequency 1, yeah, that's just one of each. We want to know when mu1 is greater than mu2. So notice our t-value, we got 1.604. Notice 1.604 t-value there. P we said was between 0.05 and 0.1. Here we can see it's definitely 0.0644. and they use, you can see the DF is not quite as conservative. Um, we're not going to worry about how it calculates that. But either way, that's how you can get there. And so, as I said before, it's bigger than 0.05, so we failed to reject. Part B, interpret the p-value you got in part A in the context of this experiment. So I would basically just say that, let's see here, what did we get for our value for there? 0.0644. So basically, the results that we got from these two samples, the likelihood of something having a difference this big or greater is about 6.4%. And again, that's assuming that assuming that calcium had no effect. If the null hypothesis is true, that would happen at least that 6.4% of the time. So, so don't use the pool. Don't worry about that. You want comparable sample sizes, and then remember at the end of 9.3, I believe we did that caffeine example. That's paired data. So on that we use one sample T procedures. So just keep that in mind. And yeah, so looking at this, to decide whether you should use paired T procedures or two sample T procedures. So looking at this to test the wear statistics of two tire brands, A and B, we got one brand A tire mounted to one side of each car, and one brand B tire mounted on the other side. So which side gets which brand is determined by flipping a coin. And then let's read B, and then we'll try and decide which one's which. Listening to music while working can listening to music while working increase productivity? 20 factory workers agree to take part in a study to investigate. Researchers randomly assign 10 workers to do a repetitive task while listening to music. The other 10 workers to do this task in silence. Okay, so A is going to be is kind of a match pairs experiment. So there we're going to use paired T procedures, and B here this is just two different samples. So we're going to use two sample T procedures. And there you have it. So that I'm going to do a thorough run through and make sure there's nothing else. But that for this year's AP test in 2020, that should conclude the new material for the school year.